about how would T optimal change of if K1 equal to K2, which is 0.25 m³ kg per second at 300 Kelvin. So from here we can know the reaction 1 is A changing to B and is K1, and then reaction 2 is B changed to C. So first we do for the mole balance on A. dFA over dW equal to reaction rates. So since reaction rate equal to K1 over K1 times Ca and Fa equal to Ca over CAV0, so we type these two equations into here and we get this one. And then after that we do integration for both sides, and finally we get that Ca equal to Ca0 e power of negative K1 down 1. So this is our first equation. So for the second one we find the mole balance on B, because B is the product for the reaction 1 and the reactant for the reaction 2. So the reaction rate of B will be the reaction rate net, and we need to find for the reaction rate B in reaction 1 and reaction rate B in reaction 2. So finally K1Ca minus K2Cb is our equation, and we sub this and this into the equation and we get this one. And then since K1 equal to K2, so we can change the K2 at here to K1, and then after that we integrating factor for this equation and we get this one. And then when tau equal to 0, Cb equal to 0, so finally we get this equation for our Cb. So for the optimum U is dCb over d tau equal to 0, and then we differentiate the equation from mole balance on B here. So we get this one, and then after that we rearrange it. So we get that K1 tau 1 equal to 1. So finally tau 1 equal to 1 over K1. Since tau equal to W over V0, we can sub the tau here with the tau at here. Tau 1 equal to 1 over K1. So finally we get that W equal to V0 over K1. So for the X optimal is Ca0 minus Ca over Ca0. So the Ca here we can start with the first equation we found just now, the mole balance on A. So after that we get this one, and then we take it out and rearrange, cancel each. So finally we get that the answer will be 1 minus E negative K1 down 1. So we sub the down 1 with this one, what we found just now. So finally we get that the answer will be 1 minus E power of negative 1, and then we change it to 0.6321. This will be the X optimal for the reaction.
So for question 2, we need to find the tau for CSTR. So we will get the mole balance where Fa0 minus Fa over the reaction rate, and substituting F flow rate equals to volume rate times concentration of A, we will get the formula equation for this. And then the tau will equals to W over V0. So substituting, rearranging, we will get formula tau equals to Ca0 minus Ca over negative Ra, and again substituting negative Ra equals to K1Ca, and we'll get the final formula for tau. Rearranging, we'll get Ca0 in terms of Ca in terms of Ca0. And for B, component B, same thing where Cb0 minus Cb over Rb, which we derive from here. And we substitute Rb will get in the form of K1Ca plus K2Cb from the reaction, and Cb0 is 0 in this case, and substitute Ca equals to Ca0 tau 1 K1 plus 1 into the formula of Ca, and rearranging will get a formula for Cb as well. So to get the T optimum, we need to differentiate Cb towards tau, and this differentiate will equals to 0. The equation will simplify into a quadratic formula, and given in the question, K1 and K2 is equals to 0.25. Substitute into the quadratic equation above, we will get an equation where 2 tau square plus 13 tau minus 4 equals to 0, and we will get the final answer tau equals to 0.2944, or a negative answer which is neglected.
So for the C, there's a given in the question which is stated that the given tau is equal to 0.5 kg per meter cube per second. and for the CA0 is 5. As provided with the K1 which is 0.4 and also the K2 which is 0.01, and it's also given for the E1 as 10 kilocal and per mole, and also the E2 which is 20 kilocal per mole. And then from the questions we have to plot the CB versus T plot, which is you will get the graph which is this shape. There will be an optimum point with the whereby the optimum point will be the optimum temperature for this reaction. So the optimum temperature we found from the graph which we plotted is a 325 Kelvin.